So exciting. I'll begin. Heavenly Father, we thank you for this day, and we just pray that you'd bless this class, Lord. Help us to understand what we can, and just learn the most from the time, Lord. In your name I pray. Amen. All right, so I have written up on the board here, because I had to go eat my lunch right quick. I forgot to eat it before linear algebra, then it dawned on me, oh, I should eat my lunch. And so I got that done, and I knew I'd be 5 minutes late. Sorry about that. So for today, and just to avoid talking about a basis choice mostly, we'll put A equal to Rn as a point set. Assume we've got some sort of multiplication on there. I'm using a star to denote the multiplication apparently, but push come to shove in an example, we won't write the star, you know. And so typically with examples, we just write it by juxtaposition, but I think the star is helpful to start with. So definition, a function from the algebra to the algebra. Here again, we're assuming that we have a unital associative real algebra of finite dimension, not assuming commutative at the moment. And so differentiability at a point means that it's real differentiable, and sorry, my sentence here, I bailed on writing it on that line, and then I neglected to erase it. So this should be gone. There we go. Is R differentiable with differential, right? DPF going from A to A, satisfying the right linearity condition, which is to say that the differential of the function as a point is in the regular representation of the algebra, right? In more detail, what that means is that the differential is right linear, right? Which means that it's really, that of course immediately implies real linearity. You know, real linearity is an easy consequence of right linearity of the over the algebra, and also that it satisfies the Frechet quotient here, right? So that's what we mean by a differentiable at a point. And then so that leads us to then define the derivative of the function at a point. The derivative of the function at a point is just the number corresponding to the differential. In more, to be more specific, that is f prime of p would be dpf of 1. That's the isomorphism between right linear maps and the algebra. We just feed 1 into it, it gives us the corresponding algebra element. But more specifically here, in terms of real calculus, this is really what? This is really dpf of E1, right? And since we're working from Rn to Rn, you could also write that as the Jacobian matrix, right? This is the Jacobian matrix, partial f, partial x1, partial f, partial x2, and so forth and so on, partial f, partial xn, the usual Jacobian matrix times E1, right? So what is that? Of course, at the point P. Yeah. Well, that's nothing more than partial f, partial x1 at the point P. So if we have a differentiable function at a point, then its derivative is in fact the same as partial differentiating with respect to x1, making the appropriate identifications. And furthermore, we can define, you know, P maps to f prime of P for all, you know, P in the domain of f for which that's reasonable, defines f prime as a new function from, you know, well, I guess I should be careful. I should say from appropriate subset of A, right, to A. And the same is true for here, right? I get, you know, this could be replaced with appropriate, you know, open subset. Okay. And so that's, we define the derivative at a point. And then we can derive the derivative function because there's a natural correspondence between the differential and the algebra, and hence between the, you know, This allows us to assign a algebra element for each point. And then, of course, we can go further than this. We can define second derivatives and third derivatives and so forth and so on in the usual way, right? Like what would f prime prime f prime prime of p would be f prime, right, prime of p. So more explicitly, that would be the differential of f prime at the point p of v1, right? So I'll get back into that in a bit. All right, so what are the properties of a differential, differentiation of the algebra? So there's lots of sort of familiar properties. If we have f and g are, so I use this symbol in my paper here, c sub a of p. This means that f and g are a differentiable in some neighborhood of p. All right, so they're a differentiable near p. Okay. If that's the case, and if c is a constant algebra element, then using the usual definitions, f plus g and cf are in CAP. So the usual definitions, I mean what, of course? Sorry not to be too boring in here, but you know what I mean. F plus g of p is defined point-wise to be f of p plus g of p, right? No surprises there. And likewise, CF is defined point-wise to be c times. I mean, perhaps, oh, what the word? Claim reward. I got to turn off these push notifications. I've got many games on my phone, so I have to figure out how to turn off the push notifications, Now, maybe this is at odds with my current notation. Maybe I should write C, C star F like that instead, because, this would be C times F of P. I mean, that's what I mean by that. It's an algebra multiplication. What I'm trying to say there. Okay, so anyway, here's essentially the proof. Using the ordinary advanced calculus, we know that the sum of real differentiable functions is real differentiable, right? So, by usual calculus, we have that dpf plus g is dpf plus dpg, right? So this is serves to satisfy the Frechet quotient, right? In other words, if I plug in, dpf, if I plug in over here dpf plus dp, dpf plus dpg of h, then I can use the usual triangle inequalities and break it up and prove that that's small, given that given the real differentiability of f and g respective. So the only thing that really remains, ignoring the advanced calculus, is to show that this is right linear. But that's almost kind of silly, right? Because that follows from the fact that these are both where? These are both in the regular representation of A, right? And the sum of things in the regular representation of A is again in the regular representation of the A. Now, if you don't believe that, of course, you can easily prove it, right? So if we take dpf plus g of v star w, in other words, we get dpf of v star w plus dpg of v star w, well, we can use the right linearity both times, right? But then we use the property of the algebra to rewrite that as, well, let me just skip a step. So we get dpf plus dpg all on v star w, right? Which, there you go, that proves that the sum of the differentials is again right, again right linear map, so there we go. Now, the one that perhaps actually merits a little standalone calculation might be the scalar multiplication, right? So let's look at the scalar multiplication. My claim would be that if we can use the linearization of c times f, right, of h. What are we, I mean, you kind of know what you're going to do, right? You're going to do c times the differential at the point we're interested in, f, right? That would be my proposal, is that we just use the scalar multiple of the differential for our, for our differential. And so if you look at c star f, right, of p plus h minus c star f of h minus c star dpf, right, of h, what do we get? Oh, goodness gracious, yes, thank you. Very good. So we can pull, I mean, basically the point is we apply the definition of scalar multiplication over the algebra, I mean, not scalar, but algebra multiplication of a function. And then by properties of the algebra, we can pull the c out, right? We got c times, f of p plus h minus f of p minus dpf of h, right? So then you take the norm of this whole thing, right? And then you use the property I proved last time, the submultiplicativity. See, this is less than or equal to what? This is less than or equal to m sub a, the norm of the constant, whatever that is, times the norm of this thing, right? Well, times the, let me just say for Shea quotient, right? Of f at p. But you're given that you can make this arbitrarily small. And so this is just a constant, and that's a constant. So you can make this as small as you like. Then by the Squeeze theorem, you can prove that we get that the linearization of c times f is in fact c times the differential of f. So then that implies, of course, that c times f prime of p is just equal to dpf, I'm sorry, c times dpf, right, of 1, which is, of course, c times dpf of 1a, which is indeed c times f prime of p, right, which is what we set out to prove. But anyway, that proves that c times f is, again, a differentiable at p, and that the formula for the derivative is the stupidest, most natural thing you could expect. Yeah. Any questions? So we have the sum, we have scalar multiple. Then the next thing you might try, of course, if you're getting greedy, is just multiple of functions, right? So what if we look at f times g, right? Is this going to be in CA of p, given that f and g are in CA of p? So let's see here. I mean, there's various, like in my notes, not in my notes, but in the paper, I actually give a kind of argument in this style, right? But another way you could argue it would be at the level of structure constants. I think that's what I did to start with, right? So what would to show that, let's see here, f star g is actually equal to what? Let's do it that way in here, since I'm kind of nostalgic for structure constants for the moment. This would be the sum over ijk, right? Of ci, jk, those are constants, they're structure constants. And then you got yourself an f sub I, and a g sub k, and an e sub k, or that's the standard basis in our current context. So what does the differential look like? So, you know, you can calculate the ith partial, let's say the elf partial derivative of this. What's that look like? So these are structure constants. So what do? They don't even see that partial derivative. I'm assuming that f and g are in CAP, which means that they're real differentiable, so the derivatives at least make sense. And so what you get, of course, is partial fi partial xl gk plus fi partial gk partial xl. And yeah, fine, it's over there. So what are we looking at here? I mean, if you rewrite it back in terms of star multiplications, that's exactly, what is that? That's exactly partial f partial xl times g plus f times partial g partial xl. Well, that's not too bad. That should definitely be J's. Both J's. Thank you. Jonathan, I think you might have a future in tensor calculus. Let's see here. It's good. Good eye. Thank you. So, I mean, great. That's a formula for the elf column of the Jacobian matrix of f times g, right? So perhaps at this point it would have paid off. Well, I don't know. See, I've worked myself into this sort of corner here. Curses. What are other ways we can characterize a differentiability at a point? I mean, let's see here. So we had dpf, right, of ei times ej is what? It's dpf of ei times ej, right? But more specifically, if we look at dpf of ei, or let's say ej, right? That's dpf of e1 times ej, right? Which is dpf of e1 times ej. So this on the one hand would be, you know, partial f partial xj by the usual advanced calculus. The jth, to get the jth column of the Jacobian matrix, we take the differential acting on ej. That gives us the jth column of the Jacobian matrix, which is partial f partial xj. But on the other hand, if we have this right, if we have that, dpf is right linear over the algebra, we also can pull like this. Now this right here is partial f partial x1, and that's multiplying by ej. So, theorem, given f in CAP, right? Well, that's not what I want to say. That's too greedy. Given f differentiable in the real sense at P, all right, so it has real partial derivatives, then f is an element of CAP if and only if partial f partial xj is equal to partial f partial x1 at the point P, of course. At P, all at P, times ej. Yes, times ej for all j. Of course, in the case j equals 1, it's just kind of silly. And here again, I'm assuming what I said at the start, which is that E1 is the identity. If E1's not the identity, then in the commutative case, you can also, so these are, of course, the Cauchy-Riemann equations, or the ACR equations, A Cauchy-Riemann equations, right? And I would make a comment. If A is commutative, then we have that dpf of EI times EJ is equal to dpf of EJ times EI, and that implies the so-called symmetric form of the A Cauchy-Riemann equations, in particular partial f partial xi at P times EJ is equal to partial f partial xj at P times EI. The symmetric, and if all of the symmetric Cauchy-Riemann equations are met, that also implies a differentiability. That's a component, a column level computation which gives you a differentiability. That's useful in algebras where we don't have E1 equal to the identity. It's more sort of like computationally convenient if you don't have the actual identity as part of your basis. Those are nice. I found those in a 1949 thesis by a guy named Fox. He takes those to be the Cauchy-Riemann equations. Anyway. All right. Okay, so my point was, we have a differentiability means what? It means that if we can take the jth partial derivative of the function and show that it's actually the first partial derivative times ej, then that gets it for us, right? Now that I've done that, I see how to make that irrelevant. So sorry. So for some reason that has unlocked in my brain the thing that was not loose a minute ago. So what's this say about the differential? First of all, observation. This is sum of scalar multiples of our differentiable functions, right, at P. Hence, f star g is certainly real differentiable at P, right? Because if we take the scalar multiple and sum of real differentiable functions, we get a real differentiable function, no matter how complicated that thing might look like. It's still a stupid real differentiable function. So we know that the differential at P, right, of f star g exists. That exists from that argument. But on the other hand, from this calculation right here, you can see what the lth component of it is, right? So, in fact, you can see from this little lemma, not too far from this, you can see that this is actually going to give me dpf star g plus f star dpg. Now, what do I mean by that? Let me be more careful. I mean, there's some ambiguity there possibly. So let me feed it a point h. Where does the h go? It goes here, right? And to be clear, that's g of p. That's f of p. That's dpg of h. Okay, they're obnoxious, but there it is. That is coming from just, I mean, if you calculate, you can calculate just evaluate this. Evaluate the left-hand side and the right-hand side. If you evaluate the left, so how do I say this, guys? dp, I don't even know if I want to get into all this detail. If you put h equal to el, right? What's dpf? What's dpf of f star g of el? By definition, it is partial xl of f star g, which I have up here. And if you calculate this on h equal to el, you get that. So these things are equal. Do you guys follow? Saying if you plug in h equal to el over here, that should give us partial f partial xl star gp, f of p star partial g partial xl. But that's exactly what I have here. I've omitted the p's, but so that's why these are equal. So this formula. Yeah, this would fall under my Uber product rule that I worked out for you guys in advance last time. My product of product rules. Anytime you have some kind of linear product over a pair of vector spaces with another vector space output, if it's governed by some fixed set of structure constants, then you have a product rule.
So we kind of like discovered that in the process of that or is that just a nice result?
Well, I have written notes proving like product rule for dot product rule for cross product rule for matrix product, and product rule for scalar multiple function, product rule for this and product rule for that. And finally I got sick of it and was like, it's always the same stupid argument. Why don't I just say, you got two vector spaces, you got some way of combining them in a linear fashion, a bilinear fashion, to output a vector space output. If you have that structure and you have component functions, you got a product rule that respects the structure. It's just, it's a general, this is a special case of that really, but anyway. But the point is, here's the funny thing. Yeah, this formula makes sense, but that's not to say, this does not imply that f star g is an element of CAP, right? Because what would it take for that to be a differentiable? You need to have right linearity of that differential. There's an obstacle to that. What's the obstacle? So if we look at dp f star g of, let's say x times y, well, that's dpf of x times y times g of p, right? Plus f of p times dpg of x star y. Well, that's great. This is what I want. Okay, no problem there. But over here, this y has to move over here. And that's the impediment. If the algebra is not commutative, I can't push it past that g. So I need the other function to be such that it commutes with everything in that way. So I need g of p to commute with all y in order to get it over there. Now, it could be that your algebra has elements in it, right? Non-identity elements that happen to commute with everything in that way. If you have such a thing and your function g is valued like that, then it's possible to have f times g a differentiable. And I have an example in the paper which I'll project in a second. I don't want to write that one out. So this is, generally speaking, this is an obstruction, right? It's an obstruction when A non-commutative. In fact, it's a pretty severe obstruction. In the non-commutative case, it can be shown, if the algebra is what's called semi-simple, that the only a-differentiable functions in that case, the only ones are merely linear functions. You don't even have quadratic a-differentiable functions in the semi-simple non-commutative case. Now, if you're not restricting your algebras to be the semi-simple ones, then there are, in fact, lots and lots of ones which are the product of which are a-differentiable. But that's more like kind of, well, that's my example is one of those things. But all right. So if we got commutivity, we're good to go on the product. But this has caused, for example, if you read Ward says that the definition that we used for a-differentiable, essentially he rejects it because the product of differentiable functions is not differentiable in his view. And so he says that it's essentially his idea that our idea of a-differentiability is wrong because of that. He insists that the product of differentiable things ought to be differentiable. And so to avoid that, he actually goes on to look at this thing called the derived algebra. And so he doesn't have to have the Jacobian lands in the regular representation. It can land in like I think the derived algebra or something like that. In which case, the regular representation matches Ward's more general thing in the commutative case, but in the non-commutative case, Ward's idea of differentiability actually differs from ours. So I really, in some sense, am more following Wagner's work. But anyway, okay. So, let me show you that example before we go on. So I should give credit where credit's due. I don't know how long it would have taken me to find this example if it wasn't for talking to Robert Bryant through Math Overflow. Professor Bryant worked with my advisor ages ago as an undergraduate at NC State back in the 70s. And I think he was president of the AMS, the American Mathematical Society, like 2 years ago. He's been the director of this MSRI thing. I think he's a professor at Duke. He's forgotten more than I'll ever know, most likely. He is. If you read Math Overflow, you'll soon learn who he is because people ask really technical, complicated questions about the differential geometry of Lie groups and other things like that, and he gives lengthy, insightful answers pretty fast. Come on, seriously? I thought I had this thing plugged in. Golly, look at that. I must have unplugged it unknowingly. I guess we'll be starting again. Let me see here where we're going. Oh, you like that? There's so many things they get upset about when we go out to eat. There's so many different things to get upset about. You don't get something another child gets. I don't know. There's so many different exciting ways to get upset. Let's see here. Oh, come on. Oh, I guess my organization here is somewhat suspect, I'll tell you that. Where's that stupid thing? I think this is what I've been looking at with you guys. Oh. I'm sorry, I know what I should look at. Nah, this is the one I want. It was in there. Yeah. Idiot. You, me, not you. Right, that's here. Be clear. You know, this observation that we can define the derivative in terms of the number which corresponds to the differential, I didn't know that at the start of this. Like, there was a month or two at the beginning of my work where I was not making that identification. So every time I differentiated, I was thinking the derivative is a linear operator. Because that's what you do in advanced calculus. The derivative of a function from Rn to Rn is the pointwise assignment of a linear transformation on Rn. Right? I can't tell you, that makes it much more complicated. When it finally dawned on me, because Spencer finally talked me into it, Spencer's like, but we could just make it a number because we can identify these things. And I finally was like, oh, duh! Thank you. It's been very helpful ever since. But I can't take credit for that. That was Spencer. Finally talked some. I would have figured it out eventually. It's been about like 3 or 4 months later, and I think Spencer got tired of waiting for me to make the leap. And so I'm happy he did that. But okay, so I was just talking to you guys about this one. Here's the. So actually, in my notes, I have. You know, I actually look at the product of p plus h valued functions and suggest that this is actually a formula for the Furché quotient of f star g, and so I work with that and actually give a rather different not. You notice the advantage of the argument in the notes is it doesn't assume any of this Rn stuff I'm doing. So this would work. It's basis independent, this argument. That's what the advantage of it. But I think it's good for you and us, for us to talk about basis dependent calculations, because that's a lot of what we're after in this course. You know, we want to actually come up with some examples and some applications that maybe we haven't thought of before, or I haven't thought of before anyway. So, so let's see here. This is assuming commutative. In commutative case, you can just pull the, you pull the w out, but then you can move the w out there, and if you multiply this out, you get that by commutivity, which shows you that the differential is right linear, right? And more than that, when you plug in 1 into the formula, you get the most natural thing you'd expect. You get f prime p times g plus f times g prime. It's just what you want in the commutative case. But in the non-commutative case, basically what's the condition we're fighting, the obstruction we're fighting against is for f and g given, we have this trouble. If there exists a w such that that happens, we're in trouble, right? So I thought, well, look at that specifically. And that's equivalent to supposing that, well, to get out of trouble, we'd need that this is equal to 0 for all w and all v, right? Which, if you massage it a bit, is the same as saying dpf times that is equal to 0, right? And, well, certainly for the constant function, it's true. Because, which was not surprising. We already proved that a constant multiple of a function is adifferentiable. So yeah, we knew that special case would work out. But on the other hand, if we have an algebra which has non-trivial solutions to this, right? And so you can talk about the center of an algebra, the set of all x which commute with everything else. You know, I've never used this. I think it would get the message after a while. No, I do not want to create a copy of my computer somewhere else that people can steal my data from. No, thank you. You guys probably don't think that way, though, huh? No. I mean, if somebody's going to steal my data, I want it to be my employer. It's here. So, oh man, now I got to edit this. Nah, no one will ever find it. All right, let's see here. So, I mean, the cost of getting to that comment is pretty high, right? And you guys aren't going to publicize it, so it's probably safe. Wait a minute. You look a little... all right. I'll go on. Anyway, the center, Well, the center is an ideal, right? In the sense it's got that uber closure, it's a subring, you know. So if g of p is in the center of A and g of p is not 0, then we find that A is not a simple algebra. A simple algebra is one that has no non-trivial ideals except for the whole algebra and the 0, right? So if the center has a point in it which is not on 0, then unless it's the whole algebra, then the it's not a simple algebra. So the reference for what I was just saying about semi-simple algebras is in Rosenfeld. Rosenfeld shows that there are only linear adifferentiable functions over simple, associative, or alternative algebras, which is something else. But anyway, here's an example of a non-simple algebra and a function, actually, in which actually what I'm going to show you is a pair of functions f and g such that f times g is adifferentiable, but g times f is not. So it's kind of messed up. So you could define, so I'm defining a multiplication on R6 by this rule. All right? So you're like, well, that's a weird multiplication. Fine. It is, but there it is. And if you look at the regular representation of such a thing, it looks like a so. This is the regular representation of that algebra by the usual calculations. And if we let the algebra have variables zeta, x1 through x6, we can define f of zeta to be and x2 cubed, x3 squared. And we can define g of zeta to be this, right? So if you calculate f times g of zeta, you'll actually get that. And if you calculate the Jacobian matrix of f and the Jacobian matrix of g, you get this and that. Now, one of these has the right pattern to be adifferentiable. One of them doesn't. I forget which. What do we got? 2x3. Let's see here. I got these ones over here, huh? Are those where they don't belong? Well, that could be D. F and G. Oh, I'm sorry. I'm an idiot. Those are adifferentiable. Get with the program here eventually. So F and G are adifferentiable. In fact, you can calculate that F times G is actually equal to G again, which means certainly F times G is adifferentiable since F and G are both adifferentiable. They have the right pattern. But if you calculate G times F, you get this. And if you look at that, it has, in the sixth component of it, it has a 1 in the second and the fifth column. And if you look back up here, there's a 0 in the second column lowest spot. So that 0 would be 1 in the Jacobian matrix of this guy, which means that G times F is not adifferentiable. This is exactly such an algebra that has a non-trivial center. It's not a simple algebra. In fact, if you want to know where I came up with this, I can tell you what this algebra actually is. It's isomorphic to the algebra formed by upper triangular matrices in R3×3. You look at the product of upper triangular matrices, it's another upper triangular matrix. And so if you look at A, B, C, D, E, F, you know, there's 3 plus 2 plus 1 components. That's 6-dimensional. Multiply those. The rule for that is the rule on R6 that I stated. And something like this matrix annihilates everything in the center. So if you use that, you can come up with the example. But it was not the perhaps the most obvious example. Excuse me. So this is more important for you, Cooper. So here we have, suppose you've got a function, u and v are open sets in an algebra, all right? And we've got a function g goes from u to v and v goes from u to a, and they're adifferentiable functions. And they're composable, right? F composed with g makes sense because of the way I set it up. Then if you look at f composed with g prime of p, it's actually f prime of g of p times g prime of p. In other words, the chain rule also works for a calculus, and here's the proof of it. So first of all, functions are first real differentiable, and we have the chain rule from advanced calculus. So we know that the derivative of the composite is the composite of the differentials. This is the chain rule level of differentials. So I already know this from advanced calculus, right? And so all I really need to check is the right linearity, right? In some sense, well, it's already immediate because we know that the composite of right linear maps is right linear. But here's the proof in the current notation. So F composed of G, V star W is this, but first we let G pull out the W because G is a-differentiable. And then this is a particular vector, so we can pull the W out using the a-differentiability of F. But then using the definition, well, then using the real chain rule, that's the differential of F composed of G of V times W. So we can pull out an arbitrary W, which shows that we have the composite is a-differentiable, and this lovely formula for the derivative. The derivative of the composite is the derivative of the outside function evaluated at the inside, algebra multiplied by the inside function. So this is, I mean, what could you couldn't ask for more. It's just what you want. Now, of course, once you know that, you can easily prove that like the power rule for natural number powers holds, because f zeta is, so for example, n equals 1, we have f of zeta equals to zeta, which is, say, f is equal to the identity. So the differential of the identity is, in fact, of course, stupidly, I mean, here's the stupid calculation explicitly. It's of course, it's in the regular representation. I mean, I guess I see, of course, this paper could be condensed down if I dogmatically insisted on using the algebra results I already know, right? So there is some redundancy in this paper, I mean, admittedly. So anyway, of course, the long story short here, the derivative of zeta, f prime of f of zeta equal to zeta is just equal to 1. It's the constant function 1, right? And if I was to look at, let's see here, I think I give an inductive argument. If I have f of zeta zeta to the n and g of zeta equal to zeta, then so zeta to the n plus 1 is f of zeta times g of zeta, which is, of course, f prime g by the induction hypothesis, right? Plus zeta to the n times 1, because the derivative of zeta, g is just the zeta, g of zeta equal to zeta. So g prime is just 1. And, well, what do you got? You got n plus 1 times that, which is exactly the power rule for n plus 1. So anyway, this argument isn't especially unique to calculus, right? You could do the same thing in calculus 1. If you know the product rule and you have calculus 1 students who know induction, you can prove that the derivative of x to the n is n times x to the n minus 1 for any natural number n. So you're like, so you can't do it then. I know, yeah. Yeah, how many calc 1 students know induction? Yeah, I don't know. But that's there. Yeah. Now, let's see here. So let's take a step back. Let's talk more about the Cauchy-Riemann equations, right? So I've said to you guys that f is an element of CA P if we have partial f, partial xi at P is what? It's partial f, partial x1 at P times EI. So what would it mean for f prime to be in CAP? What would we need then? Assuming it's twice differentiable, right? Well, excuse me, assuming that the derivative function is once real differentiable, which of course would then imply that the original function f was twice real differentiable. So I'm assuming these partial derivatives make sense. Well, we need the same, right? We need partial f prime, partial xi of P equal to partial f prime, partial x1 of P EI. But what is this equal to? How to say this? Remember what f prime was? F prime is partial f partial x1 in our current notation. So what does this actually say? And I see I have, that's not really what I wanted to do. I mean, that's fine, but I'm taking an awful long time to get there. I'm sorry, guys. So this is really what? This is really using partial derivatives commute, partial x1 of partial f, partial x, xi, right? Oh, no, I'm sorry, guys. I warned you guys that if I tried to do this in my third lecture in a row, that there would be certain consequences, and well, here's one. What I'm trying to do, you know what? Let me try a different format. Claim. If the function is twice real differentiable, if f from a to a is twice r differentiable and once a differentiable at p, then, all right, here we go. Partial squared f partial xi partial xj at the point P is in fact equal to partial squared f partial x1 squared times ei times ej. All right, let me try this. Let's see if we can do it. So I'll start out with the left-hand side. What's that mean? This is all at the point P, okay? This is partial xi, partial f, partial xj, right? But we can trade this for what? Partial x1 times ej, right? But the j has no dependence on xi, right? So if you'll allow me this slight cheat there. But then by usual calculus, we can commute the partial derivatives. Right? And then what do we do here? Well, this is by the Cauchy-Riemann equations again. Which, of course, gives me Does that make sense? And the thing is, if it works for 2, it works for as many as you like. So we can easily cross this out and say smooth. If it's smooth, if it's in the sense we can take as many real derivatives as we like, if we have it's once a differentiable, the fact that partial derivatives commute and that we can pull multiplications out like we just did implies that, in fact, once then this, oh, and by the way, I have, and f is a smooth in the sense that arbitrarily high derivatives of f are again a differentiable. This would prove that I mean, to get twice, to get that f prime is in CAP, what would I need? That I would just need to prove that dPA, right? dPf prime, dPf prime is in the regular representation of A, right? Which would be equivalent to the Cauchy-Riemann equations, partial f prime, partial x j is equal to partial f prime, partial x1 times ej. Let's see here. So this theorem concerns if we have isomorphic algebras. I sometimes use this theorem. If we have isomorphic algebras, then you can always take an a-differentiable function and sort of recharacterize it as a b-differentiable function by just filtering it through the isomorphism and the inverse in this way. And I mean, you can prove that if you look at all possible b-differentiable functions, then any a-differentiable function can be found from a b-differentiable function in this way. Like we can trade a set of questions in the A algebra for a corresponding set of questions in the B algebra. Sometimes it's helpful. But anyway. All right. So there is yet another way to talk about the Cauchy-Riemann equations, but I think before I get to that, let me just say a word about what this means. What does this mean then? This identity right here is absolutely just mission critical to one of the more interesting applications that I have in here. So if we have a smooth, suppose we have or as many times differentiable as you like anyway, function, we have this result, right? For f, sufficiently differentiable, sufficiently real differentiable, and well, we might as well just say a-differentiable. We've learned our lesson. If it's real differentiable, then it's automatically a-differentiable. If it's even once a-differentiable, and we have the following. We have the kth partial derivative of f with respect to xi1, xi2, partial xik. That's nothing more than the kth derivative with respect to the first variable times ei1, ei2, eik. So we can trade partial derivatives for algebra multiplications. And just to show you an explicit example of why that's important, I mean, so the hyperbolic, well, excuse me, complex numbers, right? So in there, we have E1 is 1. We have E2 equals to I in the usual notation, right? And so we know the equation I squared equals to minus 1. But of course, we could look at that as I times I plus 1 times 1 equals to 0, right? And if you take a complex differentiable function, right, and you could look at this, well, partial f partial x squared, right, I plus partial squared f partial